Hi, Christopher. The problems you gave me yesterday was very straightforward with the cylindrical base being the same. So any volume in there is linearly proportional to the height increase, right? So with the volume change the same, dV dt is the same, then dH dt will be just volume divided by the base. Now let me give you a more complicated problem, whereas that you have a cone-shaped container like that with water at a constant rate of 25 liter per minute. Okay, so basically, equation we have to do is whenever we look at the volume change, you look at the volume equation, right? You get the volume is equal to, on a cone, is equal to pi r squared times the height over 3. So that's a volume. Now volume change, you know that 25 liter per second is the rate of change. That's equal to dV dt, right? Now, if you want to figure out what dH dt is, so you take the derivative on both sides. Okay, that's what you want to do. So you got to plan ahead, right? But knowing that this is the volume formula, and given that angle of 45 degrees, you know R and H are related in a trigonometry tangent. R over H is equal to tangent 45, which is equal to 1, and therefore you know R equal to H. Now you can substitute here as H squared. So volume equal to pi H squared over 3. Okay? If you put the time variable in there, it's a function. So Vt at a given time equal to pi over 3 times height, third power at a given same time, right? Now, since we know dV dt, which is 25, you take the derivative on both sides, dV dt, which is 25, equal to, this is like a variable third power derivative, which is 3 times h squared times dH dt. Does that make any sense? Now you can solve for dH dt, right? This divided by the whole thing equal to dH dt. And you get that, right? So if you know this, you know that, the only thing you need to find out is the h. So this looks a little weird initially, right? So what does that mean? dH dt and then you got h squared. What is h squared? So now what we omit is here, there's a t here, right? It's a function of time, right? It's a function of time. So the rate of change changes all the time because it's not constant, right? I mean, the radius become bigger and bigger as you put more water in there. Therefore, the height was going to be slower and slower. So, so this is the importance. How do you find this? What is ht at a given time? Well, now, depending on the time, right? Do you see this? Vt volume equal to 25 liter per minute times minute, right? And you know volume is equal to this, right? So at any given time, you got a 25 t here equal to pi height any given time third power divided by 3. So you can solve for h. So that's basically what I did here. So equation here, dH dt, simplify it, right? Equal to that. dV dt, this is from the previous. You can see that's this here, right? And then we solve it here. And simplify that. dV dt, right? Equal to h squared. dH dt, it's proportional to 1 over h squared, right? So the higher the height, which is more the radius, and therefore the rate of change is inverse proportional to the height squared. Now we need to figure out at what given time what this height is. Now remember this, right? Volume, as we discussed, equal to that, and then height equal to these. That's a simple equation. Take a cube root and like that. And v is equal to what? 25t, right? So now if you substitute dh dt, which is here, right? And then pi, take the pi out, and then this is h squared basically, right? H squared. This is h squared. And then you can take cube 3 pi out and take the square into here and then multiply that, right? These can be separate here. A square, remember to put the square in there, right? And then you know v is equal to 25t. So that's that, and then alpha is just this whole constant, and you can calculate it or leave it in there. So the important concept is this. Important concept is this. You gotta get a volume. We're talking about volume. We're talking about changing volume. We're talking about the height, right? This is a confounding factor, but we know the relationship between R and H. Then we can convert this into H. Now we can see the volume change and H change in terms of volume change here, and then the height change here. But the height change here is related to this factor here, right? And then you solve for that, you know that it's inversely related to the h squared. You just need to know what time is relative, what the h is at a given time. At 1 minute, you know volume is 25, right? And then you can solve for h, right? Using this formula. Volume, given volume, you solve for h. At 2 minutes is 50, so you know for the 50, you put the 50, and then solve for at 2 minutes, use volume at 50, solve for t height, and that gives you the dh dt. So really, two important concepts: volume and the height at a given time. You know volume at a given time, you know the height at a given time, and you know that rate of change, which is constant, and you can solve for this equation. And at the very end, you can see at the very end, dh dt is equal to that. If it's at 1 minute, right, you can t is equal to 1, and then you can punch in a calculator at 2 minutes and 3 minutes and 4 minutes. Look at it at 100 minutes. This is going to be a huge number, right? Huge number. The rate of change is very small. It makes sense, right? So that's all. Call me if you have any questions.